Perfect. All right. Okay. Okay. So our first speaker will be Pratyush. If he can figure out the technology, great. So Pratyush is a professor at University of Pennsylvania. He's done a lot of great work on IOPs and other kinds of proof systems over the years. And he's going to tell us about the quest for optimal IOPs. So,
Okay. Hi, everyone. Good morning. Thank you, Nick, for the great introduction, and thank you, Nick, Giacomo, and Ron for organizing the wonderful workshop. Okay, awesome. Yeah, let's get started. All right, so the title of my talk is a little grand, but essentially, I guess what I'm going to talk about is how we could construct IOPs which achieve kind of maybe the best possible efficiency along certain important metrics. Okay? All right. Okay, so why are we here? We're all here because of snarks. I think I don't need to explain snarks to this audience, but I'll do it anyways because every talk needs a snark intro. Okay, so basically, snark is this protocol between a prover and a verifier, where the prover makes some claim that some function is, makes some kind of NP claim that asserts that some function is satisfied by some public input X and some private witness W. Okay, and it's able to do this by sending a very short proof that can be checked quickly. Okay, and the properties of snarks have led to lots of deployments, such as improving the scalability of these decentralized ledgers. In the future, maybe in private digital ID systems as well as private cryptocurrencies, right? And the reason why they've seen all of these deployments is because they have some very nice properties. And what are these properties, right? What are the properties that make them applicable to these applications? Well, there's a few that we care about. The first is what kind of assumptions that we can build these snarks on. So something like elliptic curve-based assumptions in the ROM, so on and so forth. Okay. How fast is the prover? How long does it take to actually produce this proof? How fast is the verifier? How long does it take to check this proof? And what is the proof size, right? How large is that object from the prover to the verifier? Okay. All right. So kind of the state of the art, or the standard that is developing or emerging today, is that for all the applications that people care about, people are using snarks built on IOPs. Okay, I'll talk about what IOPs are in a second. But roughly the reason for this is because these snarks built from IOPs, they kind of fare well in all of these metrics, or fairly well in all of these metrics. On the soundness, on the assumption front, they have transparent setup. They can be constructed in the ROM, and they're plausibly post-quantum, right? So they have a lot of nice things going for them. On the prover efficiency front, they're fairly fast after, I guess 10 years of effort. We've been able to construct these snarks which have very good prover time. They also have kind of state-of-the-art verifier time with things like WIR, which are faster than even maybe the best snarks from other assumptions. Maybe the only place that kind of falls short is that they have large proof size compared to other snarks, right? So orders of magnitude larger than, say, curve-based snarks. Okay. So in this talk, we'll see how to maybe address these shortcomings, improving the proof size while preserving or improving the other metrics. Okay. All right. So to see, why snarks that are constructed from IOPs have this kind of property, or have these properties, let's take a look at IOPs, right? So an IOP is basically this, we're all here because we love IOPs, but again, I have to introduce what they are. So an IOP is this interactive protocol between a prover and a verifier. The prover sends a message, the verifier responds, and this continues for some number of rounds. But unlike a standard interactive proof, the verifier doesn't have to read all of the messages, right? At the end, it can decide to query some of these messages, just read some individual symbols, and make its decision on whether to accept or reject based on that. Okay? And IOPs can be constructed or can be compiled into snarks with this kind of two-step process. In the first step, what we do is instead of sending the oracles, we just commit to them using some vector commitment. And then whenever the verifier wants to make some queries, it just tells, hey, prover, what are the elements at these query locations? And the prover responds with these elements as well as the opening proof. Okay, and this gives you an interactive argument. And then this can be compiled down into a non-interactive argument via fiat Tremere. Okay. Okay, so this is the high-level construction. I'm blazing through it because it really doesn't matter. What we really care about is how the efficiency of the IOP kind of affects the efficiency of the final snark. Okay, and here on the prover time front, kind of the efficiency of the final snark depends on the prover time of our IOP as well as the time to commit to all of these oracles. Okay, the verify time is basically the verify time is basically the time to run the IP verifier plus check these opening proofs, which scales, when we instantiate the vector commitment in Merkle trees, is basically Q log n hashes, where Q is the query complexity. And finally, the proof size is basically the query complexity times a Merkle path length, roughly. Okay. So really, the high-level picture from this is that when you want to design efficient snarks and efficient snarks from IOPs, we want IOPs which minimize the prover time and the query complexity, because that kind of optimizes all three metrics. Okay, any questions? Good, okay. All right, so let's take a look at how we design such efficient IOPs. The key tool that is used in almost all such constructions is this thing called an error correcting code. Okay, so an error correcting code is some way to take your message and encode it into some kind of redundant encoding. So you take messages in F to the K and you encode them into some string in F to the N, where F is your field, right? And we're kind of concerned with three main properties of these error correcting codes. So the first is distance. How far are these elements in the redundant representation from each other? What is the rate? How redundant is the representation? Okay, and how long does it take to encode? Okay. Additionally, just a couple of notes. In this talk, we'll only be looking at linear codes, so codes where the code words form a subspace of F to the N, and where the encoding process is a linear map. Okay, and also generally, we'll just focus on cases where delta and rho, the distance and the rate, are both constant. Okay, all right. So these are error correcting codes. How do we construct IOPs from error correcting codes? Well, it's basically, kind of a two-step process. So in the first step, what the prover does is it takes its witness and encodes it using the error correcting code and sends this oracle. And then the prover and verifier engage in some kind of protocol which reduces this NP claim, the satisfaction of this function, to some claim about the proximity of the oracle sent in this interaction to the code. Okay? So that's at a high level. You also have sometimes some other simple claims about the messages underlying these codes, but we'll kind of brush that under the rug for this talk. I think Ali's talk will cover in more detail, how to handle those additional claims. Okay, so after we've reduced our NP claim to this proximity claim, almost all IOPs, what we do is that we kind of just prove this proximity claim. Okay, so we invoke interactive protocol that asserts that the oracles that were sent in the first step are close to the code. Okay. So the step is also called an interactive oracle proof of proximity. And as it turns out, basically the efficiency of all the efficiency metrics that we care about for our IOPs kind of stem from the choice of code and the IOPP that we can develop for it. Okay. This is because kind of the first step we have nearly optimal constructions, where essentially, for example, in the Spartan based IOP, you only have to encode the witness and nothing else. Okay, kind of all of the efficiency of our IOP just comes from the encoding time of our code plus the encoding time or the running time of the IOP prover or IOPP prover, and the query complexity kind of almost entirely stems from the query complexity of the IOPP. Okay. So really what we want to focus on and what this talk will talk about is optimizing this last step, how to design efficient IOPPs. Okay, any questions? So feel free to stop me at any point and ask questions. Okay, all right. Yeah, so just to summarize, what we want is we want a code which has fast encoding time to minimize that T sub C, and we want an IOPP for C which has fast prover time and low query complexity. Okay, all right, so this observation that we want fast IPPs is not a new one, right? Kind of this goes back to the very beginning of the world of IOPs, and people have been at this effort of designing efficient IOPs, IOPPs for the last almost 9 years, right? Okay, so the first work in the space was kind of Ligero, and what it did was it designed an efficient IOPP for Reed-Solomon codes, okay, or interleaved Reed-Solomon codes, and achieved this kind of query complexity of roughly square root and an encoding time of the code of n log n, because we're using Reed-Solomon codes. Okay, so this is kind of the initial work in the space, like 9 years ago. Okay, and at that point, kind of the research community bifurcated its efforts into two directions. Okay, the first direction tried to improve the query complexity while leaving the encoding time alone, and the second effort tried to start improving the prover time or the encoding time. Okay, so on the first branch, we had a beetle sequence of works, fry, basefold, stir, whir, which eventually culminated in this lovely work from Minzer and Zheng last year, which reduced the query complexity down to kind of what's optimal. Okay, just lambda queries to achieve a soundness error of 2 to the minus lambda. Okay, it didn't really, again, optimize the encoding time at all, so encoding time is still quasi-linear, just n log n. Okay, on the other branch, people are also doing work. And here they try to improve the encoding time by moving to a new class of error-correcting codes, specifically linear time encodable codes. Okay, so things like the breakdown code or the Spielman code. All right. And while the initial works, again, they kind of just had the same query complexity as Ligero, eventually, via a sequence of works, we were able to improve this down to almost close to what we had on the other branch, so namely lambda log n, but still not quite where we want to be, which is optimal prover time and optimal query complexity. Okay, so it's kind of the state of the art until roughly middle of last year. And then kind of maybe late last year, there were a couple of works which kind of allowed us to join this fork back down and obtain IOPPs which achieved the best possible encoding time, which is O of n, and also this best possible query complexity of O of lambda. Okay. So in this talk, I'll basically cover at a high level kind of each of the milestones along this journey, starting from Ligero and then eventually moving through this lambda log n query complexity IOP, lambda log n, and finally culminating in the optimal query complexity IOP. Okay. Yeah. This is everything is just assuming fields. So the query complexity is in terms of symbols is field elements. Sorry? Oh yeah, this is kind of talking about maybe I would say efficient constructions or concretely efficient constructions. There's entire literature before this of PCP-based construction or PCP-style constructions, which achieves a different. No, I'm saying where. Am I wrong about this? Where? Oh.
I mean, I always understood that whir is O of lambda because it's like lambda plus lambda over 2 plus lambda over 4 because
those are all field elements, though.
Oh, that's what I was asking.
Yes.
Is it Bitcom?
This is field. Everything is in terms of field elements.
Right. So that's what I'm saying. So I always understood that in whir you can get O of lambda. Am I wrong, Giacomo, about that?
I think. Yes. Yeah, so you can grow the alphabet size in whir and stir, and maybe not, I don't know for stir, but at least for whir, and then you can achieve O of lambda query complexity there, but then it's not for constant alphabet.
Oh, okay, so it's not O of lambda field elements.
Yes, it's O of lambda log n field elements for whir. Yeah.
Thanks.
Okay, all right, thanks for the question, Ariel. Okay, any more questions before we start diving into kind of the technical portion of the talk? No? Okay, all right.
If you have a question, raise the hand and the mic will get to you.
It's a magical mic. Okay. All right. So let's take a look at this first step. How do we achieve even this IOPP with square root query complexity? Okay. To do this, we'll kind of start off with a very simple IOPP that basically reduces multiple proximity claims to some code C to a single proximity claim. okay? And we'll formalize this with this notion of an interleaved code, which you'll hear about quite a bit over the course of the day, okay? But basically, if you have some base code C with block length R and message space S, you can construct a T-wise interleaving of that code by basically taking your message, which is an S to the T, arranging it as this matrix, and then encoding each row of the matrix using your base code C. And this will give you kind of the interleaved code word, where each row in the code word is a code word in the base code C. Okay. So this interleaved codes there, it's a very simple construction. You just encode each row. They have some nice properties. So the rate is the same as the rate of the base code. The encoding time is essentially proportional to the, what you would expect is proportional to the encoding time of, again, the base code. But the distance is kind of worse. Okay, it degrades with the interleaving factor. At least if you consider it over F. If you consider alphabet to be kind of one column, then it has the same distance. Okay, and this is kind of where were, for example, would achieve, by doing this, were would achieve the O of lambda query complexity. But over F, it has poor distance. Okay, all right. So how are we going to construct an IOPP for these codes? Well, okay, so the claim is going to be that the prover is telling the verifier that there exists some message M such that this oracle, which is claimed to be a code word, is actually close to that encoding of M under this interleaved code. Okay, so that's the claim that the prover is trying to prove here. That's the proximity claim. Okay, and the protocol is very simple. All right, the verifier just samples a random challenge and sends this over to the prover. And the idea is that this challenge gamma is going to serve as basically a random linear combination challenge. So the prover is going to use gamma to combine all of the rows with respect to the coefficients, which are just powers of gamma, right? And it's going to send over this code word C star, which is supposed to be in the base code, and it's supposed to be a linear combination of these CIs with respect to the powers of gamma. Okay? All right. So in some sense, already, assuming things work out, we've kind of reduced our work, right? Earlier, we had this T size or T times K sized claim, and now we have just a K sized claim. Okay? All right. So to actually, make this protocol go through, the verifier does a few things. Okay? So the first thing it does is it basically samples some, random columns in the interleaved code and checks that the linear combination of the elements in these columns equals the corresponding location in C star. Okay, so in this new code word that the prover sent. Okay, so it does this enough times that it gets some guarantee that, okay, actually these two are indeed linked. So C star is indeed the linear combination of these CIs. Okay, and then what it does is the prover also sends along some message M star, which is purported to be the message underlying C star, and the verifier just checks that this is the case, that C star is indeed an encoding of M star. Okay? All right. So at a high level, you just take linear combinations along random columns and check that they're consistent with the new code word, and then you check that the code word is a valid code word. Okay, that's a high level construction. Okay. So let's analyze the properties of this. So completeness kind of follows straightforwardly, but we can still quickly go over it. Since the prover is honest, the code that it will send will actually be the linear combination. So the spot checks will all pass. Okay. And now essentially, since the code is linear, right, the prover can actually construct this M star and send it along. And if you work out the math, you'll see that this re-encoding check will also pass. Okay. So both of the checks of the verifier will pass as long as the prover is honest and the claim is true. Okay? All right. So soundness is a little bit more tricky, but still not too complicated. So in the soundness, the case is that we have that the verifier accepts, but the claim is not true. Okay, so there is at least one row which is far from our base code C. Okay. And then we can divide the soundness analysis into two cases, or maybe we'll see three cases, really. So the first case is that the sent code word is far from the base code C. Okay. In that case, the verifier will just reject because it'll try to encode M star, and then it'll get some code word which will be far from C star, and so the re-encoding check will fail. All right. So moving forward, we can kind of assume that this re-encoding check passes, which means that C star is actually close to a code word C. Okay. Now we have two cases, right? So if C star is close to C, it might be the case that C star is actually a linear combination of all of the rows. And in that case, it's going to be true via proximity gaps that this is a linear combination of these, but one of these is far from the actual code. That's going to happen with negligible probability. Okay, so proximity gaps ensures that this linear combination claim only holds or implies that all of these codes or claimed code words are actually close to the code. Okay, all right. So that's a case. Now we're left with the other case, which is basically that C star is close, but it's not close to the linear combination. And in this case, if you do some math, you can see that if you make like lambda many spot checks, these lambda many columns, at least one spot check will fail with all but negligible probability. Okay. And maybe, I don't know, you don't want to remember this expression, but we'll come back to this expression of this lambda over log 1 minus delta C. It'll reappear later. Okay, anyway, so the high-level takeaway is that this is the essentially full proof of this protocol. There's some details that you can work out, but this is the intuition. Okay, all right. What about efficiency? Okay, does anybody want to help me with what the efficiency, the query complexity of this IOPP is going to be? I've been designing a lot of slides for classes, so I'm in a pedagogical mood. Okay, we started off with one goal. What's going to be have we achieved that goal? How many symbols do I read in the spot checks? Okay, and we're all waking. Okay, it's going to be T. We're all waking up. Maybe we need to get some coffee. Okay, so all right. So the prover time is basically going to be encoding time plus the time to do the linear combination. The number of queries is going to be the number of spot checks times the interleaving factor, because we have to read all of these columns, plus the time to read this message, okay? And also read this one, this code word, okay? So now when we're encoding k-length messages, what we want is that this S times T is equal to K, right? And if you plug that constraint in, you basically get that the query complexity, this expression nu times T plus S, where nu is the number of spot checks we make, is minimized roughly when you set T and S this way, so roughly square root, okay? And this basically gives us a query complexity of K times lambda. Okay, so in this talk, generally, as I said, we're going to be using constant distance, constant rate codes. So I'll interchangeably write K and N because they're just off by a constant factor. Okay, any questions? Okay, all right. Either I've been exceedingly clear or I've already lost everybody in the audience. Okay, all right, so this is our modest goal that we set for ourselves, that we get this square root query complexity. Let's see how we can do better. Okay, so what we're going to do is we're going to reduce the number of queries by, in some sense, interleaving less. And our goal will be to achieve, in this chapter, is going to be achieve an IOPP, which gets us like a logarithmic query complexity. Okay. All right, so let's take a look at why this previous IOPP is expensive. To do that, we can see that we can actually split up the IOPP into two steps. Okay. What happened to this? Okay. So the first step is this interactive reduction, which takes our claim about proximity to the interleave code down to a claim about proximity to the base code. Okay, and this requires this lambda times T number of queries. Okay. Second step is this naive IOPP for this base code C, which is basically just re-encode and check that you actually have a code word. Okay, and this has O of S queries. Okay, and we can take this picture and abstract it a little bit, by talking about the first step is this reduction from K to K over T sized claims, and an IOPP to assert this K over T sized proximity claim. Okay. All right, so far in this previous protocol from the previous chapter, right, we took this, abstract protocol and instantiated it in a way that balanced out the query complexity in step 1 and step 2. Right, this got us our square root query complexity. Okay, the natural question to ask is, what if we didn't balance, right? What if we wanted to minimize the query complexity in one of the sides, let's say in the reduction? Okay. So we kind of now go to the extreme. Instead of setting t to be the square root value, instead of interleaving square root times, we're just going to interleave twice. Okay, so we're going to go from some 2-wise interleaving of C down to just one code word of C. Okay. So we've halved our proximity size claim. Okay. What query complexity does that give us in this first reduction step now? Yeah, it's lambda. It's like 2 times lambda, right? Because you can see the number of queries in the first step is lambda times t. T is equal to 2, so 2 times lambda. Okay, so nice. So we've really improved the query complexity in this step. We've got it down all the way down to lambda, okay? But then what happens to the query complexity in this step? It goes up, right? It goes up all the way to k over 2, right? So we've kind of actually gotten worse. The sum of the two query complexities is worse than what we had before. All right, so this is not great, right? But, okay, now I claim there's something that we can do, right? And this is kind of, what we can do is invoke the oldest trick in the computer science textbook. What is that oldest trick? Recursion, right? Instead of actually just proving this claim immediately, this proximity claim for ck over 2, we're instead going to imagine that we have another reduction, which can maybe take us from ck over 2 down to ck over 4. Okay. Oh, by the way, I've just abstracted out the codes. So ck in this case, in the protocol that we have so far, is this interleaving or interleaved code, and ck over 2 was the base code. And you can imagine ck over 2 is another code which has maybe another interleaved code of overall message length k over 2, and ck over 4 is that code's base code, and so on and so forth. Okay. All right. So now, if we had these reductions, which allow us to iteratively have the claim size every time, we can basically recurse log k times and eventually get out some constant size claim, and then we can just check that via our naive IOPP. Okay, so everything will work out. Okay, so we have now, I guess, a few questions. First, can we actually construct these reductions? Second, is this actually sound or complete? And third, what is the efficiency of this? Okay, so let's answer each of these questions one by one. All right, so what we're going to do is, okay, there's some animation mismatch, but we're going to set, imagine that we have some base codes B, okay, which have these message lengths, k over 2, k over 4, k over 1. They can be fairly arbitrary, with one restriction that I'll come to just in just a second. Okay. Then we're going to set each of these CIs, the CK over 2, and so on and so forth, to be the interleavings of these base codes B. Okay. All right. This allows us to construct the reduction as follows. Okay. So we're going to have first this kind of folding protocol, which is basically taking the linear combination of the rows of the interleaved code. And this allows us to go from a claim about proximity in the CI code down to a proximity claim in the CI over in the BI over 2 code. Okay, so this halves the claim size. Okay, so this step reduces the size of our claim. All right, but now we're kind of stuck, right? If you want to invoke this again, we need as input to it some kind of interleave code, right? But now we said that B can be an arbitrary code, not necessarily an interleave code. So how are we going to keep going? Okay, how can we invoke this reduction again? And here is where we will mention then and not talk about this beautiful idea called code switching, which basically allows us to take our proximity claim about these base codes B and reduce them to proximity claims about essentially arbitrary codes. And in particular, in this case, proximity of arbitrary or to arbitrary interleave codes. Okay, it's kind of the next smaller size interleave code. Okay, so put together these two steps, what they do is that they take some claim about interleave code of size, let's say k. They switch to an interleave to a proximity claim about the base code of half the size, and then they reduce that proximity claim down to a smaller proximity claim about the next interleave code, which is of half the size again. Okay, so we started with a claim about let's say CK, then we end up with a claim about CK over 2. Okay? All right. So again, I won't talk about code switching too much, but I'll just mention that we have, over the past, I guess, 5 years, many beautiful works which construct code switching for a vast variety of codes. So RAA codes, LDPC codes, breakdowns codes, Tensor codes, so many codes, and even things like kind of read-solvement. You can think that they have like a natural, succinct code switch in them. Okay, so essentially we have very efficient protocols for this code switching step for many codes that we care about. So really what we'll care about in the rest of this talk is basically this first step, the folding step. Okay, any questions? Okay. Yeah.
When you mentioned the breakdowns code, it's like a linear code block code, so this code switch also works for
Yes. Yes. Oh, yeah, just to I can just repeat the code. I can repeat the question
Please
for
raise your
the
hand when you have a question.
I can repeat the question for the stream or the recording is basically, does these code switches exist also for things like the breakdown code? And the answer is yes. That's via this NST25 work, which shows that they exist for LDPC codes, and the breakdown code is an LDPC code. Okay, and also I want to mention that the reductions here, they're called, I guess, IORs, which William will talk about, but you can kind of think of them as an interactive analog of NP reductions. But the high-level idea is that the prover time and query complexity is already what we want for these code switches, so we don't have to talk too much about them. We just have to focus on this folding step. Okay, all right. So IOP completeness and soundness, assuming that those folding and code switching steps are secure, which we talked about the security of the folding step, and I'm going to just assert that all those authors of those papers are probably not mistaken. Code switching is also secure. There are these composition theorems that people have developed for these interactive oracle reductions, which allow us to basically say that if the components of our reduction are secure, then the composed reduction is also secure. That also applies when we're composing these logarithmically many reductions in sequence. Okay. So overall, at a high level, just these composition theorems just tell us that recursing log n times or log k times gives us an overall complete and sound protocol. Okay. There's some details you need to take care of, but it just essentially just works. Okay. Okay. What about efficiency? Let's take a look. All right. Again, we're going to focus on prover time and query complexity. So essentially, I guess the prover time and query complexity are going to be the sum of the times in each of these steps, right? We're not doing anything special here. On the prover time front, like in each step, remember what we have to do is we have to fold the code, and we re-encode under the new smaller code. So the time is basically linear in K, or is the time to encode in K plus some additional work to do like the linear combinations and so on, and also to do the code switch, okay? But kind of the dominant cost is this re-encoding cost. And if you add it all up, kind of this cost halves at each step, because we're getting smaller and smaller claims as we go down. This means that we obtain kind of a running time here, which scales with the size of the largest code, the running time, which is of the first step. Okay? All right. This is the more complicated calculation. What about query complexity? What is the query complexity of the overall protocol? Yeah, it's just log k times the number of, I guess it's like the sum of the query complexities in each step, but this is just lambda in this one, lambda in this one, lambda in this one, and so on and so forth until the end, so you get a query complexity of lambda log k. Okay? All right. So this already this achieves our goal, but I set out for this chapter. Okay, so getting this nice prover time while going from square root to logarithmic query complexity. Okay, but remember our goal is to get lambda query complexity. So let's see how we can do that by first taking a baby step. Okay, we won't go all the way directly to lambda. We'll first go to log k. Yeah.
Yeah, but right, you have a code switching sort of proof at every step, which I think they do with some sum check.
Yes, so I said before that we're not going to talk about these additional claims that we have to prove about the messages underlying the code words, but you can essentially you know, fold those sum check claims along as well. So you can reduce those claims. You can sometimes add them to the thing that you reduce it to.
Oh, I see. So you can somehow aggregate them so you stay with the lambda log k in
Yeah,
total.
yeah, it kind of
Okay.
works out. Yeah. So I won't talk about it. I think Ali's talk will go into more detail on how you can do that. Okay, how are we doing on time? Okay, I'm running definitely very short on time, so I'll try to speed things along a little bit. Okay. All right. So yeah, our intermediate goal is going to reduce this from log k to log k. Okay. For all practical purposes, log k is essentially just 1, right? It's like 5, but it's still, eventually a good idea to get down to even remove that 5 factor. Of course, that'll only be in theory. We'll see that the protocols which have this query complexity are much more efficient than the protocols, concretely than the protocols which have of lambda query complexity. And maybe that'll be one of the open questions for the session tonight or in the evening. Okay. All right, so let's see how we can improve upon this protocol from before, right? What we can hope for is that if we want to achieve lambda query complexity, we can say, okay, I'm going to, say half the number of queries in each reduction. Okay, so the first reduction takes lambda queries, the second reduction takes half that, the next half of that, and so on and so forth until I get O of 1 queries in the final step. And then if I sum all of these up, I will just get like something like 2 lambda or whatever. Right? But unfortunately, this doesn't work, right? If you try to do this and you work out the calculation, it ends up being the case that in the ith round, you need distance which scales like 1 minus 2 to the, I guess, minus 2 to the I. Right? So it kind of grows exponentially, right? And because rate and distance they have this trade-off, once you start hitting this huge distance requirement, this means that your rate must be tiny, which means that your encoding time really blows up, which means that our prover time will go up. Okay? So kind of doing this naively in this way doesn't work, right? You can't hope to reduce the number of queries in half at each step. Okay? But we can kind of salvage this a little bit by flipping things around. Okay? Instead of setting what our target query complexity in each step is going to be, we can instead say, okay, we're going to set our distance in such a way that it kind of maybe increases across rounds, and then see what kind of query complexity we can get from that. Okay. So what we're going to do is we're going to say, okay, in the first step, we're going to have some distance. In the next step, the codes, we're going to aim to have double the, half the distance. Okay. So they're going to be more redundant. Okay. And in the next one, we're going to aim for proximity claims where the distance is even half of that, and so on and so forth. Okay, so you keep doing this over the rounds. Okay, and basically this gives you the expression that in the ith round, your query complexity is this value. Okay, I don't expect you to verify this, but it's not too. You just plug this into that expression that we had from a couple of slides ago in chapter 1. And it turns out that if you take this sum now, if you sum over the number of rounds, this will kind of give you the query complexity that we aimed for, just lambda log k. Okay? All right. But there's still a problem. Okay, we're not quite done. And the issue is that in each step, we are halving the message length, but also halving the distance, which is effectively, I guess, doubling the rate at least, right? And what this means is the code word length doesn't change in each step. So in each of these reductions, we will have the same code word length or block length of, let's say, n. Okay? And then now this kind of blows up our prover time. So we go from, the encoding time halving now just stays the same across rounds. This means that at the end, we will have this additional log factor to account for in the prover time. Okay, and we want to get rid of that. We don't want that blow up. Okay, and the idea in works like stir and whir is basically what we're going to say is that we're going to fold more. Okay, so we're going to, yes, the distance is going to blow up our code words, but we're going to fold more to account for that. So instead of folding in half, we're going to fold, let's say, in fourths, okay, or in sixteenths, or so on and so forth. So we're going to shrink the code word size more by folding than the distance amplification blows up the code word size. Okay. All right. All right. So if you plug in the parameters and calculate it out, you kind of get what you want. So we end up with our prover time being just dominated by the encoding time, plus, and the query complexity is still the same. Okay, maybe slightly worse because now you have to account for this larger interleaving factor, but asymptotically the same. Okay, any questions? I think there's a question up here.
If you fold more, will that make the distance like also change more?
No, so we're just setting the base code to be the higher distance base code, but we're setting the interleaving parameter to be, let's say, 4 instead of 2. Okay.
Okay, but
Okay.
I'm missing a little bit.
Okay, all right. I think I have 6 minutes. I don't know how I'll get through the final, I guess, opus of this talk. Okay, all right. Okay, all right. So this kind of gets us almost to our goal. We have good encoding time and hence good prover time, and also this lambda log log k query complexity. But now we can aim to chop off even this log log factor. Okay, and we're going to do that by moving away from interleaving somewhat and going towards tensoring. Okay, so we'll talk about what all of this means. Okay, all right. So our problem so far in reducing the query complexity is that we have too many reductions, right? And we saw from the previous chapter that we can't reduce the number of queries in each reduction fast enough, right? If you try to have it, your distance blows up. Okay, so what we're going to do instead is we're going to reduce the number of reductions. Okay, so we're going to reduce the reductions. All right. So what we want, basically our goal will be a constant number of reductions, each of which takes lambda many queries in such a way that at the end you have this constant size claim that you can just check. Okay. As it turns out, the goal is a little bit easier than this. In some sense, it suffices to reduce the message length just to, let's say, cube root, because at that point you can invoke, you can code switch to claim proximity claims about Reed-Solomon codes with a very bad rate and hence very good distance, and then you can invoke protocols like stir and whir, which in this regime have the query complexity we care about, just lambda. Okay, and also Reed-Solomon codes in this regime, they can be encoded in less than k time, so we're fine. It doesn't impact the overall time. Okay. So yeah, our goal is basically this kind of reduction, which takes a k-sized claim and gives us maybe the k to the 2 to the 3. I forgot it's 2 or 1 there, but it gives us a smaller claim. Okay. All right. So again, let's take a look at our reduction protocol. What we're going to do is we're going to again bump up our interleaving factor. Okay, so instead of interleaving by 2 or 4, we're going to interleave with this much higher interleaving factor of k to the 1/3. Okay, we'll see why 1/3 just kind of works out, but basically the point is that it's not constant; it's super constant. Okay. All right, we can write this just for conciseness as basically a kind of an inner product claim between the columns that we queried and the linear combination vector. Okay. But again, if you had to use this as a starting point, we're kind of screwed, right? Because the query complexity is interleaving factor times lambda. So this already both blows way past our budget. It's worse than the previous 2 chapters. So we end up in this much higher query complexity. Okay. Well, okay, so how can we overcome this? Well, what we can say is, hey, we have this prover at our disposal. The verifier says, hey, prover, can you help me in checking these spot check claims, these inner products? Okay. So what we want, in some sense, is some kind of IOP which allows the prover to convince the verifier that these spot checks hold. Okay. But okay, unfortunately, by itself, it doesn't quite help, right? And this is because to be able to be convinced of some claim, the verifier needs to know what that claim is. It needs to know what these inner product claims are. So it still has to read these columns as explicit input, right? So we've not reduced anything there. Okay. So to fix this, we could try to give the verifier oracle access to the columns instead. So just say, hey, verifier, you don't need to read the oracles in their entirety. You can just query them at random points. But this doesn't quite work, right? And that's because, let's say the prover gives oracle access to the columns, which are correct in everything except one location, right? then the verifier will never notice, in some sense, right? There's not enough distance. And then the inner product would be completely different, which would maybe allow the spot checks to pass, but the verifier would never notice. And this is, the problem here is basically that a malicious column is not too far from an honest, the correct column, okay? So, okay, how are we going to fix this? Yes, error correcting codes, right? Like it's the second tool in IOPs after recursion, okay? So what we're going to do is instead of providing these oracles in the plane, we're going to send them in encoded form, okay? And effectively what this means is that we're going to take our interleaved code and encode each of the columns as well, okay? This is what's called the tensor code. That's all the tensor code is, basically. You interleave, and then you encode along the columns as well, okay? We're going to, let's call these, I guess, the full columns mu sub j. Then essentially what we want now is a slightly more complicated IOP, which proves not only the inner product claims, but also this claim that these oracles that the prover sent are actually close to the encodings of whatever message is supposed to be. Okay? Okay, this is the most technical part, so ask questions, but not too many because I don't have that much time. Okay, all right.
So basically, we need usually we use Merkle commitment, right? Merkle tree commitment. So how to commit the encoded
You can just
tensor
lay it
encode?
out as a
You
a
pre-encode
lattice
them
in
and
Merkle tree. Yeah.
okay, okay.
Yeah. The prover, it just sends now this tensor code instead of sending the interleaved code. Okay. All right. Okay. So what is the simplest IOP? Well, the simplest IOP basically just well, it invokes some IOPP to check the proximity, and it just checks each of these inner product claims individually, right? But if you do this, you kind of are still worse than the previous two chapters, because you end up with some lambda squared query complexity. Okay, like each claim, there's lambda many claims, and each of those claims will require, like, say, lambda queries to each column, and this will be lambda squared. So it's too much for us. So what we need to do is design kind of a more sophisticated IOP for this claim. So let's focus on this most sophisticated IOP. And what we're going to do is we're going to have the prover send under some other error correcting code an encoding of all of these, I guess, these base messages, these SIs. Okay? So you can think of these SIs, if just to remind ourselves, they're basically the columns in the interleaved code. And the UIs are the encodings of those under the column code. Okay? So the prover sends an encoding of the concatenation of all of these SIs, and then it needs to convince the verifier that two things are true. First, that this code word U is actually an encoding of the concatenation. And second, that the inner product claims hold, okay, for each of these. This should be, sorry, SIs, not UIs here. Okay. So the first claim, this close to an actual encoding of the SIs, can be broken down into two further claims. The first is that U is actually close to this code D that we chose to encode it with, okay? And that the message inside the U is consistent with the UJs. Okay? So again, this is the most technical step, so stop me if there's any questions. All right? Okay. So it turns out that this claims or 1.1, 2 can be all dispatched by encoding or choosing as our code D, the Reed-Solomon code with high enough distance. Okay, so k to the half or k to the let's say with rate k to the 1/3. Okay, and this is fine because encoding is, so basically we can choose this as our error correcting code. This is fine. Encoding this is still going to be sublinear, is going to be less than k. Let's say k to the 2/3. And then in this regime with this inverse polynomial distance, work and prove proximity and some check claims in one go with just O of lambda queries. Okay, so we can basically discharge all of these obligations by using Reed-Solomon codes for that step. Okay, so all we're left to do is to prove this step, that the message inside this code word U is consistent somehow with the messages in these columns, or with these columns, in fact. Okay. All right, okay. So this is going to take, we can try 2 attempts. The first attempt is a naive attempt. Okay, so what we're going to do is we're going to go back to our favorite trick, which is spot checks. So the verifier is going to sample some random, per column is going to sample some random locations and check that U is consistent for that column at those random locations, okay? So this involves basically some claim which between the rows of the generator matrix, the ith of the generator matrix, with the jth message. Okay, I won't go into too much detail here, but the point is that if you try to do this, you end up still with quadratically many queries. Okay, this per column you have lambda queries, as lambda columns you end up with lambda squared. I also won't talk about how we prove this in a product claim. You can kind of batch it with other sum check claims. Okay, so what we actually do is a little bit more complicated, and this is where maybe most of the math in this protocol comes in. At a high level, what we're going to do is we're going to sample actually more than lambda columns. Let's say we're going to sample 4 lambda columns. And then we'll kind of subsample some checks from these. Okay, I don't think I have too much time, but I'll try to go into it quickly. So what the verifier does is she samples many, many columns for lambda. And out of these, each of these, for per column, she picks a constant number of locations to query. And ask the prover to prove that, okay, those constant locations, let's say here and here, are consistent with the encoded or the underlying message, okay, by multiplying with the generator matrix row. Okay, so you can kind of think of this process of multiplying with the generator matrix row as a kind of a batch code switch. Okay, so this kind of works. The query complexity is just 4 lambda. There's 4 lambda columns. Per column, we're making constant number of queries. We get this overall nice query complexity, okay? But this is actually sound, right? Seems like a kind of unnatural thing to do compared to everything else that we've done so far. I guess I don't have too much time to go into it, but at a high level, the idea is that if our distance of the column code is half, then out of these 4 lambda or 4 new many columns, right, the number of bad columns which are far from the code is going to be tightly concentrated around the average number of bad columns, which is, let's say, 2 new. And this follows from some kind of churn-off bound, right? And this, as a corollary, you can basically know that at least lambda of these columns is bad, okay? Now, if I sample a constant number of queries per column, right? And each bad column is at least half distance away from the code, then the prover can get caught cheating in each bad column with, let's say, some constant probability, okay? Some constant probability per query, and there's constant many queries, okay? Now, combined with this corollary, this basically, now we have a lambda number of checks, each of which fail with constant probability. The probability that none of these checks fail, which means the prover avoids detection, is going to be negligible, okay? And yeah, if you set this new appropriately, this whole thing becomes negligible, okay? So it's kind of like the high-level idea behind both of the works which achieve this optimal query complexity. But yeah, the takeaway is basically that if you do this, the prover time for this step is as we expect, okay? It's just the encoding time plus lambda. Okay, I'm getting dirty looks from Giacomo next. I'll quickly wrap up. So basically, I guess, in this talk, to summarize, we covered this journey from square root many queries all the way down to kind of the optimal number of queries while improving the prover time also, okay, over n. Right, so I only have 50 minutes to cover all of this, right? There's a lot of details which I skipped over, which some of the talks from today's workshop will cover in much more detail, right? So yeah, we should go to all of those. And also, like, there's a lot of details in the papers. But kind of this is a high-level summary of this kind of little journey that we've taken over the last 9 years. Okay, thank you.
Thank you, Pratyush. I guess questions we'll have to take offline. So Dan's talk is next and will be in the adjacent room, not this room. Thank you. Yeah, good. Yeah, really nice. Yeah, yeah.